here is the references to the papers, my name is Georgy Prokhorov, and I will speak about my results with Oleg Chiral and Valentin Zakharov. We present a Joint Institute for Nuclear Research from Dubna and Institute of Theoretical and Experimental Physics from Moscow. In my talk, I will discuss some aspects related to manifestations of quantum field theory in hydrodynamics. I will discuss the properties of accelerated and vertical fluids. As it was shown in the previous talks, just in this case, some quantum field theory laws manifest themselves. Here you can see the contents of my talk. I will start with introduction and will say some words about quantum field theory and hydrodynamics. I'm sorry that I don't have time to speak about many interesting results in this area, so I will say you only some well-known facts which are important for me in my today talk. Then I will go to discussion of different quantum aspects of acceleration and vorticity in hydrodynamics. And first we'll discuss effects of acceleration and we'll speak about so-called emergent conical geometry in the Zuborev density operator. And in the second part of my talk, I will discuss chiral vertical effect and its relation with gravitational anomaly for spin 1/2, spin 1, and high spins. And at the end, I will give the conclusions. Let me start. Now we know that in non-central collisions of heavy ions, huge magnetic fields and huge angular momentum arise. More accurately, we need to speak about not rotation as of a rigid body, but differential rotation, which is different at different points. And in this way, we come to the concepts of vorticity and vortices. And for illustration, the corresponding rotation in non-central collisions is extremely fast. It is 25 orders of magnitude faster than the rotation of the Earth. However, acceleration is also very high. It could be expected from the very beginning because the acceleration is just another component of the same tensor as vorticity. And also it was shown that acceleration gives the contribution to polarization, which is similar, which is of the same order as the contribution of vorticity. So acceleration is also very high. And I also want to mention that there are other mechanisms to generate acceleration in heavy ion collisions. In particular, there was an idea to consider acceleration related to the tension of the hadron string. In this case, acceleration will be extremely high. From the theoretical point of view, I think this is maybe one of the very important achievements just of the 21st century, is that it was shown that fundamental laws of quantum field theory, such as quantum anomalies, manifest themselves in hydrodynamics. Here I give the well-known formula for chiral anomaly, which has a gauge part and also a gravitational part. And it was shown in many papers that existence of this anomaly leads to interesting effects in hydrodynamics. In particular, this leads to chiral vertical effect. And Moreover, it was shown that the gauge part is related to the terms with chemical potential in vertical current, while gravitational part of the anomaly is related to effects of temperature. So this is the well-known formula for chiral vertical effect. The relation with gravitational anomaly first was shown based on the holography, and then there were the papers in which the same relation between gravitational anomaly and chiral vertical effect, temperature part of chiral vertical effect, was shown in four-dimensional space by considering the radiation from the horizon of a black hole. Previously, it was shown that when we consider black hole, gravitational anomaly is not important around the black hole, but becomes significant on the boundary of this black hole or at the horizon. And it was shown that just gravitational anomaly on the horizon of a black hole generates Hawking radiation. And then in this paper, an analog of rotating black hole was considered. And in this case, gravitational anomaly leads to the flow of chirality, which is in full accordance with the temperature part of chiral vertical effect. I will come to the discussion of these aspects in the second part of my talk. And the main conclusion from my introduction is that the appearance of the vertical current of chirality is a direct consequence of the chiral quantum anomaly. Moreover, we know, this is a well-known fact, that magnetic and electric fields are related to each other in electrodynamics. In the same way, vorticity and acceleration are also related to each other. So we can ask the question, what are the quantum effects in hydrodynamics in the case of acceleration? This is just the question which was discussed in the previous talk. We also can ask the question, what is the relation between quantum anomalies and chiral vertical effect in the case of high spins for spin 1 and high spins? And what is the relation between anomalies and higher order terms in the current, such as the cubic term in vorticity and mixed term with acceleration and vorticity? And now I move to the next part of my talk, in which I will concentrate on the first question, and will explain why we can say about emergent conical geometry in the Zubarev density operator. Here I give some information about Zubarev density operator. It was already discussed in the previous talk. This is the general form of this operator in global equilibrium. And we are interested in this term, in this operator, which accumulates information about vorticity, about thermal vorticity. It looks like the contraction of thermal vorticity trends and generators of Lorentz transformations. This term can be expanded in terms of boost and angular momentum. And then it becomes clear that boost is related with acceleration and angular momentum is related to vorticity. And I want to notice that in this context, temperature and acceleration are independent parameters. So different temperature ranges can be considered in an accelerated medium. And maybe it is not so trivial because it is in contrast of Unruh effect. Because in the case of Unruh effect, we usually consider Minkowski vacuum, and in this case, the medium temperature is related to acceleration. So these two parameters are related to each other, and this connection is fixed by the well-known formula for Unruh temperature. So we are interested in quantum effects of acceleration, and for this purpose we need to use this operator, and we can use perturbative approach and expand this operator in Taylor series in this term. Then we obtain such a series, and in every term in this series we need to find correlator with the product of boost operators in the case of acceleration, and the operator of the quantity which we are interested in. In this way, different quantities can be calculated, and we were interested in mostly energy momentum tensor. And before us, the second order terms were found in this tensor, and we calculated fourth order terms in this expression. And for this purpose, it is necessary to find 5-point correlators from this series. And we considered different cases, case of direct fields, scalar fields, complex and real, massive and massless fields. And here I give the results right away. This is the mean value for energy momentum tensor of massless Dirac fields, and this is the value for massless scalar fields. And here is the fourth order corrections, which were also presented in the previous talk. And it can be easily shown that these unusual numbers allow us to show that energy momentum tensor vanishes at the Unruh temperature. And this is, as it was first noticed in this paper, is the way to check the Unruh effect from the point of view of quantum statistical theory. So we can say that we have checked the Unruh effect, and moreover, we can say that the corrections with acceleration in energy momentum tensor are controlled by Unruh effect. And also, again, I noticed that these are perturbative results, and now there is the next step, and non-perturbative calculation was made, which is in accordance with these results. However, the same phenomena can be considered from quite another point of view by consideration Rindler coordinates of an accelerated observer. This is the well-known formula for the matrix in Rindler coordinates. Since we are interested in effects at finite temperature, we can pass to imaginary time, and then this two-dimensional part of this matrix corresponds to the space on the surface of the cone. The cone has a singularity at the vertex, so this space-time is called space-time with conical singularity. And the properties of this conical space-time are related to thermodynamic and hydrodynamic quantities. In particular, an angular deficit of this cone is related to acceleration and temperature. And if we consider some point on this cone, then the distance from the vertex corresponds to inverse acceleration, and the circumference corresponds to inverse temperature. So this matrix corresponds to Euclidean Rindler space-time, but this is not the most well-known example of the space-time with conical singularity. The most well-known example is a space-time of a cosmic string. However, it is equivalent to Euclidean Rindler space-time In particular, it can be easily shown that the second diagonal component of energy momentum tensor in a space-time of a cosmic string corresponds to the energy density in Euclidean Rindler space-time. So here I present the known results for the space-time of cosmic string for mean value of energy momentum tensor, for scalar and for Dirac fields in terms of the characteristics of cosmic string. However, then these expressions can be transformed to Euclidean Rindler space-time and can be expressed in terms of temperature and acceleration using this dictionary. And finally, we obtain these expressions which are in full accordance with the expressions which we obtained from the Zubarek density operator. And the same coincidence also can be checked for more general massive case. So we can say that the duality of two approaches has been discovered, the duality of statistical and geometrical approaches. But despite the correspondence of the results obtained in these two approaches, theories are different. In statistics, based on Zubarev operator, the perturbation theory was considered for effective interaction with the boost generator. And the linear coordinates were not used in any way, unlike the geometrical approach. Also, if we speak about vorticity, it was shown that effects of vorticity are controlled by anomalies. I already told about this in my talk. However, now we can see that acceleration effects are controlled by another fundamental effect of quantum field theory. Acceleration effects are controlled by the Unruh effect. However, as I already told, in the sequence of papers, it was shown that the Unruh effect also follows from the gravitational anomaly. So we can make a prediction that the acceleration effects are also controlled by anomalies. And in this way, they are similar to the chirovertical effect and the effects of vorticity. And now I move to the second part of my talk, in which I will focus on chiral vertical effect. Here again, I present the slide which I already shown. Here is the chiral anomaly, and I want to remind you that gravitational part of this anomaly controls the temperature part of chiral vertical effect. In fact, if we follow to this paper, which considers the radiation from the horizon of the rotating black hole, then the coefficient in the gravitational anomaly is proportional to the coefficient in the chiral vertical current for Weyl fermions. So the result of this paper is that the correspondence of statistical and gravitational approaches with the gravitational anomaly on the horizon was shown. And now one can ask what will be for higher spins. The first higher spin is spin 1. There are different definitions for chirality for spin 1. But maybe one of the oldest definition is magnetic helicity, which looks like this. And other definitions are also discussed. One can look this paper. And many years ago, it was shown that there is a chiral gravitational anomaly for spin 1. So the expression for this anomaly is similar to the expression for the anomaly for spin 1/2. However, the coefficient in this anomaly is 4 times bigger than for the well fermions. And using the technique from this paper, it can be shown that this factor 4 will lead to 4 times difference for temperature part of chiral vertical effect for photons in comparison to well fermions. So this is the prediction of gravitational anomaly in terms of this paper. However, in different papers using statistical approaches, it was shown that this difference between photons and well fermions is true, not 4. So this difference between predictions of statistics and gravitational anomaly looks like a problem. And here I give some comments about possible sources of this problem. First, it is necessary to notice that both for magnetic fields and for rotating systems, we may consider Landau levels. And this is the formula for Landau levels in magnetic fields. In particular, from this formula, it can be shown that there is a zero mode when energy is zero, and this zero mode is important for chiral magnetic effect. However, for the rotating case, due to the fact that gyromagnetic ratio is 2 times smaller, then there is no zero mode for spin 1/2. But this difference can be compensated for spin 1 because spin will be 2 times bigger. So again, for the rotation, for spin 1, the zero mode appears, and maybe just this is one of the source of the difference between the predictions of gravitational anomaly and statistics. Another aspect is related to the question of regularization. In particular, in this paper, it was discussed that we need to use some infrared regularization. In particular, it can be done by introduction of the boundary for the rotating medium. And then we have one more parameter, which is the radius of the cylinder of the rotating medium. And we have 3 parameters. And in this paper, this assumption about a relation between these parameters was considered. However, one can consider also other assumptions, and it is not clear what will be the results in this case. Maybe this is also important for the coefficient t² for spin 1 chiral vertical effect. And finally, I want to notice that in particular from the Zubarev operator, we can show that there are third-order terms in chiral current. There are mixed terms with acceleration and vorticity. And if we use the duality between temperature and acceleration following from the Unruh effect, then one can expect that this a² omega term will modify the coefficient for t² term. And moreover, this may lead to cubic dependence on spin, which is important as it will be shown on the next slide. We can also go to higher spins. In the case of higher spins, the gravitational anomaly is also known for many years. This is the expression for the gravitational anomaly for arbitrary spin. This factor -1 corresponds to the difference between bosons and fermions. Here is a cubic dependence on the spin. And actually, this expression is used in supersymmetry, where higher spins are considered. And it was checked in particular case using other methods, in particular for spin 3.5. And using this expression, we can again predict the coefficient for chiral current for arbitrary spin, which will look like this. It is in accordance for spin 1/2, but already leads to the difference, which I discussed on the previous slides for spin 1. And if we look to this formula, it can be noticed that this cubic dependence was not obtained in statistics. In particular, in this paper, there is a prediction for chiral vertical effect for arbitrary spin, and for the same statistics, there is linear dependence. And this cubic dependence is another source of the difference between gravitational anomaly prediction and statistics for spin 1. And also there is one more difference between predictions of anomaly and statistics corresponding to higher order terms. Parity allows appearance of 3 types of terms in chiral current. Let's consider spin 1/2. And these coefficients can be calculated in different ways. We calculated them using Zubarev operator. And in this case, we need to find such correlator with boost and angular momentum operators and operator of chiral current. And here I give the results for chiral limit. It is important that there is no such term with scalar product of vorticity and acceleration, because as it was noted previously, this term breaks the conservation of chiral current. And these 2 other terms were calculated. And here I give the full formula, which also was presented in the previous talk of Andrea. And here we have cubic corrections in vorticity and mixed correction A square and omega. First, I want to notice that these higher order terms depend on the boundary conditions, which were not taken into account when deriving this formula. The importance of boundary conditions for higher order terms is discussed in different papers, for example, in these papers. However, this formula matches the result in the literature. In particular, the correction A square omega exactly corresponds to the results of another approach in this paper, while this correction cubic in vorticity also was obtained in different approaches and also matches the results of other papers. However, as it was noticed in paper of Stone, the prediction of gravitational anomaly for this cubic term in vorticity is different, and the result is 2 times bigger. And this looks like another case of difference between predictions of gravitational anomaly and statistics. And as it was noticed in this paper, maybe this is related to the issue of boundary conditions. So a more thorough study of the issue of boundary conditions is necessary to solve this problem. And now I go to the conclusions. So the quantum corrections with acceleration in the energy momentum tensor for scalar and direct fields, massive and massless, were found. It is shown that these corrections are controlled by the on-roof effect and match the predictions of field theory in space-time with conical singularity, in particular in the case of space-time of cosmic strings. Also, there is a difference between predictions of the gravitational anomaly and statistical calculations in the case of the chiral vertical effect for spin 1 and for higher spins, and we discussed some sources and possible solutions for this problem. And also there is another difference between predictions of anomaly and statistics in the case of higher order terms. In particular, in the case of third-order corrections in the chiral current. And I would like to end my talk with the next statement. The physics of chiral phenomena is looking for manifestations of the fundamental effects of quantum field theory and general relativity in hydrodynamics, and opens up a unique opportunity to study quantum anomalies on the present experimental level. Thank you for attention.
Thank you, Georgy, for this nice talk. And I now, so now there is time for questions. And so I would like, okay, so I see 2 raised hands. Shugwang?
Yes. Can you go to the page where you show the gravitational anomaly for arbitrary spin? Maybe page 25 or 26, I don't remember.
Yeah. You mean this? Yes.
I still, yeah, maybe it's due to the connection, but
yes.
It's yeah, maybe because my connection is not that. Oh yes, okay, yes. Can you remind me how is this S cube term arise in your case? Because in our derivation we do not have this term. We have only
actually the derivation of this formula is not trivial if we look at the papers of Duff or Duff, because for higher spins physics becomes much more complicated. There is the question of ghosts, and they give contribution to this anomaly. So unfortunately, now I cannot say what is the source of this cubic dependence, but this is the result of this complicated.
Okay, that's fine. That's fine. I can check those papers. Okay, thank you.
Next question by Victor Ambrus.
Hi, George. Thanks for a very nice talk.
Hi, thank
you. I have a question regarding these higher order terms that you highlighted, which are cubic or fourth order with respect to acceleration and vorticity. Yeah, for example, on this slide. So my question is something which is puzzling me. What is the physical interpretation of these terms? Let me please give some context before asking the question. So one can consider that there is a system of fermions which undergoes some kind of motion, rotation or acceleration or both, which is put in a thermal bath at a finite temperature and a finite chemical potential. So the question is, once we remove all the fermions, that means we set the temperature to 0 and the chemical potential to 0, one should recover the vacuum state. And in this formula, sending T and mu to 0 would give a non-vanishing result, which means that these 2 terms here are actually some vacuum contribution.
Yes, I agree, but maybe I cannot add something new in comparison what is written in your papers and papers of Vilenkin. So this looks like some vacuum contributions, but actually maybe it can be compared to similar vacuum contributions in energy momentum tensor. There are contributions like a power 4, so they look also like vacuum contributions. And there are the papers in which these vacuum contributions are called Casimir energy, which is related to the existence of the horizon for the accelerated medium. So I don't know, but maybe some physical interpretation related to Casimir energy can be used also in this way, but I'm not sure that I can answer now.
Yeah, I guess my question is whether, for example, in an effective theory like hydrodynamics, one would like to use these expectation values computed using quantum field theory. Should these terms be included in the conductivities, or should they just be left out as some vacuum term which is not physical?
Unfortunately, I don't know, but what I can say is that, as for me, these mixed effects, especially when we have acceleration and rotation, they are very non-trivial. And but okay, we again have here the cubic term with vorticity, but I don't know how can we use them for effective field theory.
May
This
I
is a good
comment?
question.
May I comment on that?
Please.
So that we, as far as I, as you have seen from Andreas' talk, that these terms are also recovered in this approach that Andrea presented. This omega squared and a squared. However, it should be noted that these terms arose in a theory where you do not enforce a boundary condition at some finite radius on the fields. In other words, that if no constraint on the boundary value of the field is enforced, that you have this problem of acausality. So, namely, that physically you have something which is moving at a speed higher than the speed of light at some large enough radius, which in turn has a profound consequence on the statistical operator, which it has no longer a vacuum. So it means that the operator in the exponent is no longer bounded from below. And this is at variance with the Unruh case, where you have acceleration. This is because in that case, you have factorization in two causally disconnected regions. So I doubt that these terms are physical.
Thank you. Let me just make a final comment on this issue. There is a, let's say, solution which was proposed many years ago, maybe almost 40 years ago, by Ayer, which is to change the definition of the vacuum in order to implement a system which undergoes rigid rotation. And this definition of the vacuum is based on the idea that the particle spectrum should consist only of modes which have a positive co-rotating energy, which is in contrast with the Minkowski vacuum, which has particles for which the particles have positive eigenvalues of the Hamiltonian. So this change of vacuum somehow removes all the vacuum contributions which are obtained in the QFT calculation.
Yeah, it is. Of course, you may regularize this with, for instance, with the prescription that you just quoted. However, the problem, I think, remains. So, as you know, I mean, this was also noted in the Vilenkin paper, which is quoted in the slide. That
yes,
if you enforce a boundary condition on the field at some finite radius, then you have not miraculously, but you have, because of some say mathematical property of Bessel functions, then you have everything is fine. and there is no problem of negative corrosating energy or something like this. If you don't do that, on the other hand, you have. And this is, of course, leads then to some, say, maybe physical terms like those. I mean, I don't know. Certainly, it is a long-standing problem, as you pointed out. So you maybe can regularize this problem by in the different ways. But certainly, I believe that the most physical, so the most, I would say, the neatest way to do it is to put some boundary condition on the field.
Yes, I agree with the comments of Francesca. So another aspect is that, as we discussed previously, for the effects of boost and acceleration, we know that these corrections with acceleration lead to vanishing value of the quantities at the en route temperature. But in this more complicated case, when we have both vorticity and acceleration, it is not clear what will be the analog of this condition, which was in the case of pure acceleration, because you can see that this quantity is not zero at the room temperature. Maybe if we understand this condition, then we will understand the meaning of these terms.
Okay, thank you.
So one more question. So there are two more questions, Giorgio and then Lin Shu, and then we move to the roundtable discussion.
Perhaps this is a sort of a question in the discussion because it's related to the last question. Is there a sense? I mean, if you consider field configurations, is there a sense that the KMS condition is satisfied because you have temperature, acceleration, and rotation, which of course are mixing? And if it isn't, in what sense is it equilibrium? I mean, if acceleration and W go away, you still have temperature and chemical potential, but the acceleration and the rotation aren't necessarily in equilibrium with acceleration and chemical potential, right? So is the KMS condition satisfied?
I think that it is satisfied, and maybe it is related to the fact that if we consider evolution operator for the medium with acceleration, then it can be shown that this evolution operator includes not only Hamiltonian, but combination of Hamiltonian and boost. And this leads us to correct KMS conditions. So maybe there is no any problems.
For a general temperature, a general chemical potential, and general WNA, is there sort of a frame where it's satisfied?
Maybe I don't understand your question very well. So
it maybe we'll continue in the discussion. It's yeah.
Yeah, I think it's a good idea. So let's ask Lin Shu to ask the last question.
Okay, thank you for the nice talk. So I have a question on the acceleration again. So actually, so I thought, I mean, acceleration is similar to vorticity. Vorticity has a bound on the spatial radius. So acceleration also have a bound for the temporal direction. In the temporal direction, it cannot take too long, otherwise it exceeds speed of light. But actually now, your result and also Andreas shows another bound for the acceleration. It is set by the temperature of the medium. So if the acceleration is too large, the energy density becomes negative. So how this en route relation temperature arises?
I'm sorry, I understood the first part of your question in which you told about similarity of vorticity and acceleration. And then you ask how the en route temperature rises or what?
I'm saying there's another bound, right? When the acceleration is too large, the energy density becomes negative. So this bound is set by the temperature of the medium.
Hmm.
And this via the en route relation between acceleration and temperature. So could you explain physically why there is such a bound?
I can say that actually this condition which was mentioned that the value of the quantity is 0 at the en route temperature, it was predicted previously. So this is direct consequence of the en route effect. So I think it is clear. If we use these formulas beyond the en route temperature and go to lower temperatures or higher accelerations, then of course energy density and other components of energy momentum tensor will be negative. However, there are some signs that when we go beyond the en route temperature, physics changes qualitatively. And the form of these expressions for the quantities will be already different. This is the first notion. And the second notion that actually the negativeness of energy, maybe it is not a very big problem. It was already discussed in other contexts. For example, in the case of so-called super radiance. And in this case, predicted the way to obtain energy from the rotating black hole. So in the same way, we can expect that negative value of energy leads to some instability, to some unstable properties. But what I want to note is that this region of negative energies, region of temperatures below the en route temperature, is very little studied. I hope that I answered your question.
Okay, thank you.
Okay, so that, yeah, maybe I can add something to this. That there was a, so it was in the question, it was said that if you wait long enough, so if you have a uniformly accelerated system, then if you wait for a long enough time, then you get a violation of causality. But this is a uniformly accelerated comoving. So the acceleration is constant in the comoving system. Therefore, this never happens.
Yes, exactly. In this case,
So
proper
there is no
acceleration
causality.
is constant. So
Yeah.
the speed
And,
is always less than speed of light.
yes, sure. And the fact that the fact that the density of the energy density vanishes at the en route temperature is in perfect agreement with the en route effect, which states that if you have an accelerated system, then this sees the thermal radiation. Therefore, the temperature cannot be lower than A over 2 pi. That's the point. So in fact, when you T equal A over 2 pi corresponds to the Minkowski vacuum, where T mu nu is supposed to vanish. Okay, so I have a question myself, too, but maybe we can postpone to the roundtable discussion that I would like to start. And so, first of all, thank you to Georgy for this nice talk.